Now the second part of using Galaxy, we will download some data from the SRA database of NCBI. SRA stands for Sequence Read Archive, and it's where NCBI stores data in Fastq data. So I just type here SRA NCBI. I have to say that it's not necessary to do that, because Galaxy has an option to get data directly from the SRA, but since I want to demonstrate how to upload data from your computer, I will just first download them, make them a bit smaller just to speed up all the analysis, and then we will upload them to Galaxy. So I will use the dataset SRR507778. This is yeast. It should be paired and read. It says here that it's Illumina HiSec 2000. However, if we go to the abstract and details, then we see that probably this is PacBio sequence. So I'm not sure what exactly it is, if it is Illumina or PacBio. When I mapped this dataset, it seems that the fragments are longer, so perhaps it's really PacBio. Okay, in any case, we will download the dataset. So we see here some details, and I really recommend that you go through the details and you read what people have done and what kind of data you have. So here we have paired and reads. Go to the run here, the SRR code, and then we can use this link here to download the FASTA file. So I have done this already, and therefore I will go directly to my terminal just to demonstrate what I have done. You don't have to do that, because you can download the data from here directly. It's not very large file anyway, it's 600 megabytes, so this is something that we can handle. Okay, so here is the Fastq file for the first mate of the paired end file. So whenever you see 1.fastq like this one, it means that it's one of the two pairs, one of the two mates as we call them. So this is the typical Fastq format. The first line starts with an at, and then we have the sequence, and then we have a plus, and then we have the quality reads, and we see, for example, that here the second nucleotide has been read with very low quality, and that's why there is an N here. Then they start the second read up to here, and so on. And these are really short reads, 36 base pair reads. So this is the first mate, and this is the second mate. To speed up the whole process, I have taken only a part of this file from NCBI. So this 4M means here that I have taken 4 million lines, and since every read comprises 4 lines, this means that I have taken only 1 million reads. So 1 million reads forwards and 1 million reads reverse. Okay, so I have this data stored in my computer in this directory here, and I'm going to go back to Galaxy to load them. I will go to clean history, and I specify here that I want to upload data. Upload from computer, The upload service and galaxies are quite smart, so some things can be auto-detected and you can leave them unspecified. So here I want to choose these two files. It will take some time to be uploaded, so let's come back later. Okay, now data is uploaded already. So close this, and we see here that soon it will show us that the two datasets have been uploaded. We can already view this one, so if I click here on this eye, it will show a part of the dataset. It's the same that we saw previously. And now we'll also put some name here in the history. I will just call it demo used. Fastq mapping. Okay, and let's wait for the second mate to be uploaded. Now the next step is to go for the quality control checks. Okay, so I will just type here fastqc. It's a standard tool that we use for quality control. Unfortunately, it doesn't help if I will type here quality control, because as you will see, I don't find anywhere here the fastqc. And QC is just too small to search for something. So fastqc, yeah, it writes here read quality reports. I don't know why it's written in this way. Anyway, we choose this tool, so loading tool, and then we can choose the errors that we have. Maybe I can choose both of them. So even though I can input both of them simultaneously, it informs me here that this is a batch mode input field. Separate jobs will be triggered for each dataset selection. Okay, I don't have any contaminant list. This is useful when you search for, you have ancient DNA, for example, here, which may have reads from microbes, so you put some microbes here, and then it will detect in the report of the quality control that you have microbes, for example, microbial DNA. So this is also how the middle parts of Galaxy works. It tells us information about what we have loaded on, and then we can also choose some parameters here. I will just leave everything with the default value, and I will just click on the execute. So select the files and then execute. So it's right here, executed fastqc and successfully added 2 jobs to the queue. And then here I have to wait, so the job is not finished yet. The data and the command have been loaded to the server, and it informs me here that this job is waiting to run. So let's wait for a while. You see, when it starts to run, it becomes pink here, and you have this cyclic bar to go around and around, and noting that something's going on here, so that the job is running already. So fastqc is complete now, so I can click on the view. This not, it's in text format, so this is not very helpful. Let's see here the web page, because this is the raw data used to make the web page. Okay, and this is what I need. So as we said in the class, we need a high quality score base percent reach, and here everything is high quality, actually very high quality reach. If usually what you see is that in the beginning and at the end of the read the quality drops. So just to be a bit more detailed, here on the x-axis you see every base pair position on a read, and since here all our reads are 36 base pairs long, we can go from 1 to 36. And in position 1, for example, you see the median or the quality, the distribution of the qualities of these all of these reads at position 1. So if I take all the reads and exactly the position 1 and I write down the qualities, then I will have all the values here that are represented with this box plot. And probably it informs me here that the lowest quality is 38 and the highest quality is 40, and median probably is 40, and so on and so forth. So we see that towards the end we have a few reads with lower qualities, but the total quality of every read probably is very, very high. Okay, this is the first plot. Second plot here, I don't know exactly what it is. Let's go to the third one. So this is the per sequence quality score. So this is a distribution of quality scores for every sequence. I have in total 1 million reads, and we can see here, for example, that more than 600 reads have a quality score 38 or 39 maybe, so very, very high. Fewer reads have quality 38, and then some 37 and some 36, so this is average quality score. So on the x-axis here is the mean sequence quality score. So we get a sequence, we get the quality scores for every base pair on this sequence, on every read. So we have 36 base pairs on a read. We find the average of quality scores for these 36 base pairs, and this average is one value. And then we do the same for all reads. So we have 1 million average quality scores, just because we started with 1 million reads. And the distribution of these mean quality scores for all these 1 million reads is shown here. So we see very clearly that our reads, the majority or most of our reads actually, or more or less all of our reads have a quality score, average quality score more than 32, which is very high. And most of our reads have a quality score 38, 39. So we are good. Now we see some other statistics. For example, we see here the sequence content in terms of ACGT. Okay, so here A and T is more or less 30% and CG is more or less 20% each one, which means that is probably is 80 reach, as we see here. And then we see the distribution of GC content for all our reads, and the distribution is like that, which means that if we about 120,000 reads out of 1 million have GC content approximately 38, 39, 40%. Very few reads have a GC content 67%. So very GC rich, right? And very few reads have a GC content of about 15%. Very GC poor. So this is the theoretical distribution, and this is what we observe from the data. Probably this is something yeast specific. Now per page n content, n specifies that we have a bad read, low quality read for a base pair, so we cannot detect if it is ACGT, and the sequencer reports n, and we see that this is very low everywhere. And then here is the length distribution. All our reads are 36 base pair long, so that's why we see this peak 36 exactly. We have a few reads that are duplicants, so it seems that a few reads are exactly identical between themselves. We see that here, and even a few reads are triplicates. This might be a PCR artifact, or might be pieces of sequences that are that exist multiple times in the genome. I don't know the specific things about yeast, so let's say that it's PCR artifacts. There are no overrepresented sequences. Sometimes there are overrepresented sequences if there are repeats, several, or if we have some contamination, or if we have primers or adapters left in the sequence. There are no adapters here. No adapters have been recognized, either Illumina or Nextera or Solid, and probably this because they have already cleaned the adapter from the reads. So that's all. Everything looks very good. It's quite rare to see that all sections here are ticked. Sometimes you see that you have a lot of sequence application, but it's not really so important. So we go on.